curious, observant tone. Look at a hammer thrown through the air. With its heavy metal head and long wooden handle, it creates a chaotic, tumbling blur that seems impossible to track or predict. But the physics engine of the universe ignores that messy shape. Instead, it calculates the path based on a single, perfectly balanced coordinate. While the physical body wobbles around this internal anchor, the point glides forward in a perfectly smooth, mathematically pure curve. Locating this center of mass reveals how the universe will push, pull, and rotate that object, regardless of how complex its shape might be. Mathematically, the center of mass is the weighted average position of all the matter inside an object. If you have a dumbbell with a heavy lead weight on one side and a light plastic weight on the other, the balance point shifts away from the physical middle, pulling directly toward the heavier mass. Place a support directly underneath this shifted point, and the upward push perfectly cancels out the downward pull of gravity. The object achieves physical harmony and rests without falling. But if that exact center of mass is left unsupported, gravity uses it as a mechanical hook. It pulls straight down on that specific coordinate, generating a turning force called torque, which forces the entire object to rotate. Calculating this coordinate allows engineers to map the rotational effect of gravity with mathematical certainty before they ever build a prototype. An object remains perfectly stable only as long as its center of mass sits directly above its physical base of support. Tilt it until that point crosses horizontally past the outer edge of its base, and you hit the tipping point where gravity takes over. Unlike a rigid block of steel, human bodies are dynamic. When you raise your arms or bend your knees, your mass redistributes, which means your center of mass physically moves around in real time. High jumpers actively manipulate this shifting balance point to clear heights that seem biologically impossible, using a technique called the Fosbury flop. By launching backward and severely arching their spine into a tight C shape, the athlete redistributes their weight. This forces their center of mass outside their torso. Because of this, their limbs clear the high bar while their center of mass travels underneath it. By intuitively hacking their biological center of mass, humans can literally elevate their bodies higher than their own center of gravity can actually reach. We can exploit this same balance point mechanically. Take a standard bicycle wheel and suspend it by the axle using a single piece of string on just one side. Because the center of mass hangs in open air, gravity pulls down on that coordinate, generating torque that forces the wheel to collapse. But if you spin the wheel rapidly first, its angular momentum interacts with gravity to trigger precession. Instead of dropping to the ground, the center of mass is pushed sideways. It begins tracing a slow, perfectly flat horizontal circle in the air, effectively refusing to fall. By converting a downward fall into a stable, spinning orbit, engineers can control the orientation of complex systems, from sensitive laboratory gyroscopes to deep space satellites. Scaling up to the size of a city, manipulating mass becomes a matter of survival. Hyper-tall structures like the Burj Khalifa catch immense lateral wind forces that try to push their center of mass past the tipping point. To survive this, architects installed tuned mass dampers. When gale force winds push the structure to the right, a massive steel pendulum inside the upper floors physically swings left, shifting the building's overall center of mass to completely cancel out the torque. Conversely, engineers design high-speed vehicles, like race cars, to hug the ground as tightly as possible. By dropping the center of mass within inches of the asphalt, they shorten the torque's lever arm, ensuring the vehicle remains stable through sharp turns. Whether hanging hundreds of tons of steel in the sky or flattening a chassis against a track, human engineering relies entirely on controlling this single hidden coordinate. This mathematical rule scales all the way up to orbital mechanics. Earth and the International Space Station both move around a shared center of mass known as a barycenter. This shared orbit applies to entire planetary systems. Massive gas giants like Jupiter exert an immense gravitational pull directly back on their host stars. Because Jupiter is extraordinarily heavy, it pulls the solar system's barycenter completely outside the Sun's physical surface. As Jupiter travels its orbit, it continuously pulls this external coordinate, forcing the entire Sun to trace a circular wobble, a movement astronomers use to detect hidden exoplanets. From a tumbling wooden tool to the gravitational dance of distant galaxies, The center of mass acts as the mathematical anchor that brings order to the chaos of the universe.